You can unmute or I can read from Slack. We'll make it. In the interest of time, let's move along. The first talk will be by Wenri Min.
Hi everyone, this is
The first talk will be by Wenri Ma, Santo University, on the partnerships between advertisers and publishers. Could the folk in Berlin please start the video?
Adao Xu from Zhejiang University in China. Today I will present a study of the partnership between advertisers and publishers. First, I will briefly introduce some background about the online advertising, and then I will talk about our data collection methodology, and finally present some major results. We know that online ads are very important to the internet ecosystem because they are the main revenue source to the internet giants like the Google, Facebook, and Amazon. And also they are the revenue source to millions of the websites and the mobile apps. We are the users and we benefit from the online ads too, because we can enjoy the free online content and the services. So how the ecosystem works? There are four parties involved. The advertisers, like the Nike and Adidas, they want to advertise their product online. Then the publishers, like the websites and the apps, they want to host the ads to earn money. And then the ad networks, like the Google AdWords and the Facebook ads, they connect the advertisers to the publishers. The last one is the users. The role of the user in the ecosystem is that each time a user visits a website, then that website will request ads from ad networks. When a user clicks on one interested ad, then the advertisers will pay for that click to the ad network. Then ad network will pay a share to the publisher where the ad is displayed. So we can see that in the system, nearly every party benefit from the user click. The reason we started this study is based on our own experience. Years ago, as an advertiser, we launched ad campaigns with one major ad network. However, we were disappointed at the ad campaign report because it doesn't contain some important information like where all advertisements has been displayed, as well as what ad networks has been chosen by my peer advertisers. So the goal of this study is to understand the pairing between the advertisers and the publishers in the real world. Specifically, we want to understand what's the characteristic of the publishers, whether they are similar or dissimilar to the advertisers, and what's the advertisers' preferences on the ad networks, and also how much traffic that ad campaign can really contribute to a advertiser's website. As for the data collection, we relied on a service called the SimilarWeb. Given a website or a advertiser's website domain, the SimilarWeb can return the following information. First, where these advertisers' ads are mainly displayed. So what are the top publishers? The second is the what ad networks has been used by this advertiser. The third, what's the percentage of the incoming traffic has been contributed by the advertising, by the other advertising campaign, as well as other information like what's the category, what's the rank, the country, what are the visits in the past 6 months. We validated the data by comparing SimilarWeb to Alexa in terms of the website ranking and we also use the Tranquil as a baseline. And we found that SimilarWeb is just as trustworthy as Alexa in terms of the website ranking. Because we didn't find any services like the SimilarWeb that provide the advertising related data. So we cannot do the comparison on those kind of data. So we assume those data is also trustworthy. In summary, we collected information about over 34,000 pairs of the advertisers and publishers, and they are from 119 countries, and they fall into 30 categories. Next, I will present our main results. First, which publishers got the ads? And this figure shows the top 20 categories of the publishers who got the most ads. You can see that they are the news and the media, the computers and the technology, the TV, movies and the streaming, and online social networks. We conducted the further analysis. We found that the publishers who got the ads are either very popular, such as in this figure. Those categories, they can attract most of the visits because they are so popular and there are so many visitors, so they attract the most ads. Or the publishers have the same category as the advertisers, so they can get the ads. So statistically, we found that the publishers are more popular than the advertisers. They can attract more user traffic, and it makes sense because the advertisers want to display their ads on some website which are more popular than themselves. Also, we studied the advertisers' preference on the ad networks. We found that we identified almost 200 ad networks. And here are the top 20 most popular ad networks. We found that the Google Display Network is the most popular one, and its share is almost 1/4. And then the scheme links about 10%. And we found that not so many advertisers stick to just one ad network. And we also analyzed what kind of advertisers rely on the advertising most, for the traffic. And we found that the adult, the romance and the relationships and the gambling advertisers, they rely on the advertising most. In conclusion, we studied the practice of pairing between advertisers and publishers, and our study produced insightful results for advertisers to learn more about their ad campaigns.
Hey, thanks. And you work video? So I'll watch the Slack for any questions. In the meantime, I, of course, have one in my back pocket, which is you came up with a new data set, which is cool. What do you most wish it had, which it doesn't have? Could you find these things elsewhere and correlate, etc.? In other words, what do you regret the data set doesn't have, even though it's new? Do you have your mic working? Could the elves please help? Henri, can you get on
It just
that?
looks as if the offer is not present.
Okay. Then moving right along.
Today, I'm going
Oops, the next talk is Anis Magsudlu, who is a PhD student at Max Planck in Saarbrücken, and she's looking for internships. And the talk is on tracking down the sources and behavior of port zero traffic in the wild. Can we turn on video,
going to
please?
share with you our experience analyzing port zero traffic in the wild. So you might wonder why port zero? Well, almost 30 years ago, RFC 1340 has reserved port number 0 for both UDP and TCP. However, today, in a large European IXP, we see 720 terabytes of traffic using port number 0 in 1 week. This made us curious and we wanted to investigate it further. And this is what we actually did. So we looked at the IXP data containing IPFix flows. We observed a significant number of packets having both source port and destination port equal to 0 in both UDP and TCP. Most of these packets contained payload, and they set TCP flags to 0. So we decided to contact IXP operators, and they confirmed that their flow exporters actually zero out missing UDP or TCP headers in non-initial fragments. And they also agreed that packet fragmentation is possibly responsible for port 0 traffic in this data. So in the IXP, packet fragmentation seemed to be responsible. However, we wanted to see whether we have other causes for port 0 traffic in the wild. And in the IXP, we didn't have full packet header, and we needed to take a look at other data sources. So we took a look at MAVI dataset. This dataset spans over multiple years, and the good thing about MAVI is that we have full packet header information plus some amount of payload. So we classified payloads seen in port 0 traffic using libproto-ident. And in the plot, you see that the y-axis shows number of packets and the x-axis shows year. If you take a look at the plot, you see in 2008, we have the BitTorrent as the most prominent application using port 0, while in 2012, we have DNS. In some other year, we have also other applications. So applications using port 0 change over time. However, if you take a second look to the plot, you see that the dark blue line, which shows BitTorrent, is actually contributing to multiple years. So BitTorrent is a constant contributor to port 0 traffic in different years in this dataset. Now in this plot, we don't see packets without any payload, while they make up a high fraction of the packets in the port 0 traffic. So we wanted to investigate it further with looking at other packet headers. This is why we took a look into the TCP control flags and TCP streams. We found that a large fraction of the TCP streams are one-way. And among those that were two-way, we categorized TCP streams into 4 important categories, namely scan to close port, scan to open port, no SYN, and not scan. Scan to close port is when the client sends SYN and receives reset ACK, while scan to open port is where the client sends SYN but receives SYN ACK. Then the client sends reset ACK. No SYN is where the client doesn't send any SYN or we don't capture any SYN. And not scan is where we see SYN in the stream, but there are other combinations of flags. We don't see any SYN ACK or reset ACK in these streams. So if you take a look at the plot, you see TCP stream categories by year, showing on the y-axis number of streams and on the x-axis years. In this plot, you see the light blue bars actually are the most prominent ones, and these shows scan to close ports. So a major fraction of two-way streams are scans to closed ports. Now, if you take a second look, you see that the dark blue lines are also there, showing scan to open ports are also contributing to port 0 traffic in Mavi dataset. If you take a look at 2009, 2020, 2008, you see different fractions of port 0 traffic being scanned to open port. So we wanted to make sure whether we have open port 0 in the wild, and this is why we did active measurements. We wanted to confirm that there are hosts with open port 0 in the wild or not. So we analyzed responsiveness of IP addresses to port 0 probes using ZMAP. We sent probes to both IPv4 and IPv6 addresses, both in UDP and TCP. We found no responsive IP address to IPv6 UDP probes, and most of the responses were in TCP compared to UDP. Now take a look at this plot. This plot shows the distribution of number of ASs containing responsive IP addresses to port 0 probes. On the y-axis, you see the ECDF, and on the x-axis, you see number of ASs. This plot shows that more than 40% of the responses come from only one AS, and more than 70% of the responses come from 10 ASs. So there are actually open ports 0 in the wild, but they are not evenly distributed. This might indicate that some of the networks actually filter out port 0 traffic, but the distribution of responsive IP addresses are still uneven. That said, we have actually analyzed different causes for port 0 existence. Fragmentation seemed to be responsible for port 0 traffic in the IXP. BitTorrent was also partly contributing to port 0 traffic in Mavi dataset. Scanning was also another contributor. Now in the Mavi dataset, we also saw scan to open ports, which made us to do active measurements to see whether we have open ports in the wild, and we found that there are actually open port 0 in the wild, but the distribution of the responsive IP addresses to port 0 probes were uneven. Finally, we performed periodic port 0 active measurements, the results of which are available on our website. Thank you very much for your attention. With that, I conclude my talk and take questions.
Thank you very much, Hannes. I really like this paper. We're waiting to see if we get some. Here's Mark. You want to speak, Mark, or shall I speak for you? Mark says he not sure he understands the significance of port 0 other than there's a bunch of traffic. If you looked at port 1, would we see the same thing? What's special about port 0? What are the implications of this traffic?
Okay, so do you hear me?
Yes.
Okay, first of all, thanks for the question. Well, in a like in our previous project, we took a look into the top port numbers that we saw in the IXP, and we saw that port 0 is port 0 was the only port number, the only common port number that we couldn't justify the existence. We didn't use port numbers. Port number 1 or something like that in the top 10 port numbers, but we saw port 0. So it's actually being used, although it's reserved. So we took a look into it, and so what was, I think the question has 3 parts, what's special about port 0? So the special thing about port 0 is that it's reserved. Port number 1 is not reserved, and so a lot of attacks can be done in this port number because we have there might be different firewall rules, or there might be so some network admins might ignore this port number because they don't think of it simply or something like that. I think that's the significance of port 0.
On some networks in which I work, there's a significant amount of port 0 traffic. Raphael asks, is there any distinctive feature of the ASs that accept port 0 traffic?
Okay, so for example, in our active measurements, I already mentioned that we had one AS responsive to like more than 40% of the traffic. I checked that one AS, and that was like that was 3M company, which I think most of the communication, like or ISPs or some other providers, will filter out port 0 service because they are going to protect their customers or something like that. But so one AS that didn't do that was this company. Maybe they didn't think of it, or I don't know for what reason. But yeah, that's what I think about this. Did I answer your question, Rafael? I
He's
hope so.
feeling inhibited. So I'll toss one in. What is it about BitTorrent? Is there a protocol or software fix needed?
We actually looked for, like we actually searched for this to see whether there was a problem with BitTorrent or not, but we couldn't find anything. And we also performed some experiments on our own using BitTorrent, at least one BitTorrent client. We didn't see port 0, but what I assume is the reason behind this is maybe there is a like misconfigured BitTorrent client which is producing this kind of traffic.
Oh, okay. Since there is so much port 0 traffic, which you believe to be fragmentation, fragmentation is legitimate, I believe. So is it worth telling ISPs not to drop port 0 in transit?
You mean maybe that fragmentation data contain important information?
Fragmentation is legitimate, is it not?
Yeah. No, this is only about the flow exporters in the IXP that we studied. This doesn't mean that they are coming with port number 0. This is simply empty transport header, which the flow exporters translate to 0 when they want to store it somewhere. So it's not real port 0 traffic. It's something that we only saw in the IXP because of their flow exporters.
So it's the flow exporter creating bogus data, because as Mark points out in the chat, fragmentation should be the original ports.
Yeah.
Okay,
so
Shane,
I think,
go ahead.
I think there was another first question from Matthias, like about the application classification, just to not to forget about that. Shall I answer this?
Yeah, go for it.
Okay, so we used, so actually first when I looked at the data, looked at the payload, I saw some common payloads. I didn't only take a look at the port numbers because we are taking a look at port number 0, but in the payload I saw some similar patterns. And I understood that this is like taking a look at the specification of BitTorrent. I understood that this is BitTorrent, but this was not enough for us because I couldn't do manual check for everything. So we used libproto ident and we trusted them. And this is how we did the application classification. And this libproto ident doesn't use only port numbers; it also uses the payload. So yeah.
Much discussion of what is real in the port 0 measurement of fragments. Matthias says, thanks. The change of the header quad and especially TCP, especially flags in times over the longitudinal data set, did you correlate it all with general gossip about what attack tools and flavors and fashions were happening over those years? Right? The BitTorrent we expect because it's a real application transport, but the SYN attacks, et cetera, seem to change over the years. Is there a fashion that you could detect?
Honestly, I couldn't detect a fashion, but like there were different attacks. Maybe not of a very high amount, but there were anti-peer reflection and, as I said, sin attack. But I didn't find a pattern over the years.
Okay, so let's see. Marcin says back in the days, port zero scans were used to fingerprint operating systems like using Gobbler. Do you see operating systems respond differently to port zero scans?
Okay, so we did an analysis of the TTL in our trace route measurement. If you take a look into the paper, and so some operating systems might set the response TTL to something special, for example, 64 or something like that. But we didn't find any meaningful connection. Like we couldn't prove any of these fingerprinting. The techniques. But for details, you can take a look into the paper.
Discussion of what causes port zero packets, and is it interesting that they exist? Oliver says no router is fragmenting packets on the path. What happens when a router's ingress and egress has different MTU? There are people who run jumbo on segments who have neighbors who don't.
So is it a question for me? I didn't get it, sorry.
Do you believe that kind of behavior?
Fragmentation?
Yeah.
Sorry, I don't get the question.
You can just join the chat discussion.
Yeah, okay. So let me take a look.
Couldn't flow exporters reassemble the packets? Yes, they could. Do they? No.
Yeah, that's true. So this is not something that I have control on for sure, but I think that takes more CPU, or I don't know for what reason they don't do this. They only just dump it to the IPFix data that we have. And we can also, yeah, go on.
Let me step up a level on what's going on in the chat is, are fragments legitimate in the flow today? Are there enough tunnels causing MTU changes, jumbo frames hitting 1,500 segments, etc., that we should, and do we have enough questions about reassembly that we should encourage operations to allow the fragments through instead of some people are dropping them, like firewalls tend to drop them.
Yeah.
Do you have a recommendation in that space?
So I can't say whether or not they should drop the fragment data, but like I think if they try not to have fragmented data, that would be better. I think this is a really deep discussion, which is like a very just a part of our study. But yeah, I think fragmentation in the IXP was not something that caused a big problem. It was only us taking a look at the data and see this is this was interesting. It wasn't like, I think it wasn't causing a problem from our perspective, at least. But yeah, the main takeaway from our work is that some of the networks are not actually filtering out port zero, but I think if they do, it will be better, because we see I also saw some bogus traffic, like misconfigured packets. For example, we had UDP packet length error and this kind of stuff in the traffic. So I think the main takeaway from our work is just know about your rules or your firewall rules, and maybe like filter out port 0.
Yeah. So I think everybody says don't get distracted by fragments. This was just an artifact.
Yeah.
Okie doke. Let's thank you very much. And let's roll to the next talk.
Hi, my name is Alex Martyr.
Okay, from Alex Martyr from UCSD CADA on cloud interconnection. And roll the video again.
Hi, my name is Alex Martyr. I'm a research scientist at CADA, and I'm going to be talking about our work looking at and these cloud WANs, at least for the very large public clouds like Amazon AWS, Microsoft Azure, and Google Cloud, which is the one I've got on the slide, they're really interesting. These are global networks that traverse oceans and have points of presence on every continent. We had 3 goals for this work that will help support the research we plan to do in the future. First, we wanted to find the cloud WAN interconnections for each of the 3 major public clouds, and we wanted to compare our results against some form of validation to improve. Second, cloud WANs allow you to set up virtual machines in different geographic regions, and the map on the right shows all of the different regions that we used to conduct our experiments. We wanted to figure out if clouds rely on Tier 1 and Tier 2 ISPs differently depending on where in the cloud the traffic originates. And when I say rely on, I mean handing off traffic to a Tier 1 or a Tier 2 network, either as a transit provider. Finally, we wanted to figure out where the clouds interconnect with each other. So we geolocated the interconnections that we found between the 3 major. Since everything we do relies on accurate cloud WAN interconnection inference, we first came up with an easy and repeatable way to validate our approach using Azure hostnames. Unlike AWS and Google Cloud, Azure router IP addresses have DNS hostnames, and Azure includes a tag in many of their interconnection hostnames containing the name of the neighbor. In total, we found 214 unique tags embedded in the host names for 419 addresses, and we manually Obviously, this type of validation has a few limitations. Most importantly, we only validated interconnections for Azure, and it's less accurate and complete than validating with network operators at. However, it does have the advantage of being easier to reproduce when developing new techniques or checking analysis. And in the future, we plan to work with network operators at the clouds to validate our. So now that we have a form of validation, we're ready to start experimenting. We set up virtual machines in all 32 Azure regions that were available to us. And each virtual machine sent a traceroute to every /24 covered by a prefix announced into BGP at a rate of 5,000 packets per second. All of this probing took about half a day. Then we used Border Mapit to identify the network operator for each router observed in our. When we compared Border Mapit's network operator inferences to our validation set, they matched 87% of the time. And we realized many of the mistakes occurred for one reason. Our validation dataset contains Azure IP addresses on routers operated by neighboring networks. But we observed a lot of IP addresses from Azure's address space that followed our validation addresses. There's a few possible reasons why that could happen, but we're pretty sure that path changes in the cloud WAN corrupted some of the trace. Our theory is that sending traceroutes in the conventional way increases the chances of path change corruptions. In our experiment, we use Scamper, which is a wonderful tool that uses conventional traceroute probing. It sends probe 1, waits for the reply, then sends probe 2. This means that the only way to achieve our 5,000 packet per second rate is to parallelize across traceroute destinations, leaving lots of traceroutes in flight at any given time. If the WAN changes paths, it could potentially corrupt any of the traceroutes currently in flight. Our solution was to change the way we probed so that we sent probes without waiting for replies, leaving only one traceroute in flight. Overall, our fix improved Border Mapit's router operator accuracy from 87% to 97%. And after the change in traceroute probing, we no longer saw any Azure IP addresses following an address in our validation. All right, so that was the first goal. And the second goal was to see how cloud reliance on Tier 1 and Tier 2 networks changed depending on the source region. And this is especially interesting for Azure and Google Cloud, who use cold potato routing, where they try to hand off packets as close to the destination. To do this, we set up virtual machines in every region of AWS, Azure, and Google Cloud, and each virtual machine conducted a traceroute to every /24. And then we ran Border Mapit to infer the router operators and Cloud WAN interconnections with neighbors. Next, we computed what we called the cloud transit degree for each cloud neighbor network. The cloud transit degree is essentially a count of how many networks the cloud reaches through a specific neighbor. So in the example, the cloud reaches 4 networks through AS1, giving it a degree of 4. And while the cloud only hands off traffic to AS5 when the destination is in AS5. So it has a cloud transit degree of 1. And we computed this metric separately for each region. So essentially we computed it separately for each. On the right is a summary of what we observed, and the paper goes into more detail. Basically, we found that clouds use Tier 1s and Tier 2s at different rates depending on the source region, indicating that the next hop network depends at least in part on where traffic originates. And the graph also shows that the clouds still rely heavily on ISPs to reach most internet networks. But we didn't try to determine if specific ISPs were transit providers or peers of the. Okay, so that was the second goal. And the last thing we tried to do is to geolocate the interconnections between. Our basic strategy was to use IXPs as landmarks. Each cloud appears to peer extensively at IXPs, and we know where these IXPs are since that information is listed in PeeringDB and IXPDB. When a cloud interconnection IP address shares a common predecessor in our traceroutes with an IXP address, we infer that the interconnection occurs in the same city as the IXP. This is because we expect that the common predecessor is likely on a router co-located. And here I've plotted all of the interconnections we could geolocate. The takeaway here is that the clouds appear to interconnect with each other all over the world, and often all 3 clouds will interconnect with each other in the same cities. I should note that while we could geolocate all of the interconnections between AWS and Azure, and between Azure and Google Cloud, we could only geolocate 34% of the interconnections between AWS and Google Cloud. Most of those interconnection addresses did not share a common successor with. So to wrap up, we were able to improve Border Mapit's inferences for the Cloud WAN interconnections from 87% accuracy to 97% accuracy, mostly due to just changing the way we sent traceroutes. We also found that the clouds use Tier 1 and Tier 2 ISPs at different rates depending on where the. And finally, geolocating the Cloud WAN interconnections showed that the clouds interconnect with each other in cities all over the world. All right, so thanks for listening, and I'm happy to take any questions.
Thank you very much, Alex. Having serious audio dropout is a very sneaky way to force people to read your paper. Did the problem with TTL inflation on Google Cloud, did it go away permanently after February?
So
are researchers safe now?
I mean, it hides just as much as it used to. I mean, it hides almost as much as it used to from what I can tell. what I noticed is now it seems more predictable, or at least it's easier to predict, because so in the paper, I didn't go into this into the talk really, but in the paper, I ran into the problem where even using the premium tier in Google Cloud, I was seeing traceroute paths start in neighboring networks, and this could be further along the path. So hop number 1 of the traceroute path wasn't an address in Google Cloud's WAN. And then while I was preparing the camera ready from the same virtual machines without any change, I started noticing that that hops 1 and 2 or hop 1 would be in Google Cloud, and then I would get a bunch of stars, and then I would see what used to be hop 1. So it seems like some change happened in between submitting the paper and the camera ready. But I can't say much more about what that means for researchers.
The audio is still kind of breaking up. Do you see Lars's question, or shall I read it?
Yeah, I can see it.
Lars asks, Yap, if he remembers correctly, randomizes probing order to reduce the likelihood to run into rate limiting. How do you circumvent rate limiting with FAST?
Yeah, so the only protection I have against rate limiting is the probing rate. And what I'm relying on is I randomize the targets of the trace routes, and I rely on the cloud WAN. I rely on the probes dispersing quickly after the virtual machine throughout the cloud WAN. Because the cloud WANs work differently than what I think a lot of us are used to with traceroute probing, where usually the first few hops are always they're always the same, regardless of where the traceroute path is going. But in the cloud WANs, from what I can tell, your probes seem to disperse very quickly. So they all hide the first few hops from the virtual machine, but then after that, routers start responding, and you'll see a bunch of different hops very, very quickly. So that's how I tried to address rate limiting, is that I just sort of relied on packets going in a bunch of different directions.
Spread it. Okay, Andra asks, she wonders if she could use your methodology to measure the distance from the mobile edge to the cloud. Have you looked at how the clouds connect with mobile providers?
I have not looked directly at how they connect to mobile providers, and I think it's an interesting question. I started looking at IXPs, but I haven't looked at mobile edge directly either in Europe or the US.
Okay. Oops. Nitinder asks, did you find any interesting insights about cloud ISP peering in your analysis? Certain e.g., certain ISPs directly peer with only certain cloud providers, but not all three.
It's the type of analysis I didn't include in this paper, but it's certainly an interesting direction to look at. I think we would all expect that the large ISPs probably peer with all 3 of these major clouds, but there will certainly be some networks that only peer with some and not others, and some of it will have to do with just the definition of ISPs. Are we talking about networks that maybe provide transit for a handful of other networks, at least according to what we can learn from BGP paths? But yeah, I think it's an interesting direction.
Ethan has a 2-part question. Ethan, can you speak or shall I read? Ethan asked, did you find that BRD Mapit provided substantially different results than simpler techniques? His IMC 2020 paper had similar approach for identifying when interconnections validated against all Azure and Google peerings. We found it gave identical results to BRT, MAPIT, and I'm wondering what recommendations, best practices should be.
Yeah, I think I think there's two different things going on. One is looking at neighboring networks to the cloud, and there you might find similar results if you're using just simple longest matching prefix, or if you use something on top of that. Border map it in this case was useful because we were trying to find the addresses used for the interconnections, because we were trying to number one, for the geolocation aspect, we needed to find the actual point of interconnection. But for other pieces of the analysis, we wanted to know, okay, Azure interconnects with this network with this address. So when we see this address appear in a path, whether or not we would be able to correctly infer what's going on with longest matching prefix, we now know that that address is the interconnection between Azure and one other network. So that factored into what we did with the cloud transit degree, where we tried to figure out which networks were of higher importance to the cloud WANs than other networks.
Thanks, Alex. Going to have to cut it so we have time for the next talk.
Thank you.
Hi, everybody.
Really appreciate it. Yep.
My name
So,
is Nate, and today
next-
I'll be presenting our work characterizing the security of endogenous and exogenous desktop application network flows. Understanding how applications use the network affects the security of the user, the system, and the enterprise. Understanding at scale if desktop applications use the network securely is hard because the application provenance of a given packet is rarely available at a centralized collection point. As we kind of see in this picture below, applications generate their own network traffic. At the device level, we can see which applications are generating what traffic, but as that goes to the network, we lose that detail. By putting our collection point on the host, we're able to maintain that granularity. And our second challenge is that we need to be able to differentiate between the things a user does versus the things the application does. We call this exogenous versus endogenous traffic. This is a term we borrow from biology, where exogenous would be something that comes from outside of some organism, where endogenous would be something that comes from within. There's a number of research questions we explore in this paper. We're going to focus on 3 during this talk. How many of an application's connections are endogenous? What applications are not using secure ports? And are applications communicating with reputable domains? So first, let's talk through how we did this. So we started with 24 hours of data from about 40,000 IT-managed devices on a Fortune 500 network. These devices generated application and OS configuration information, as well as application labeled NetFlow. We collected both of these things and put them into our anonymizer process that removed all human identifying information. From this set, we got 3.2 billion flow records over this time period. We also collected DNS queries from all of these hosts at a central point in the network. We only kept the resolved IP and domain pairs, so there was no human identifying data in there, and so that just continued on through our pipeline. We had 9.5 billion PDNS pairs from this time period. We then went into our enrichment, join, filter, and analysis phase. We restricted traffic down to only macOS devices and to apps that had significant prevalence in our population. Overall, it took us 4,200 CPU hours and 37,000 gigabyte memory hours to process and analyze this data. There was a lot of it. So getting back to our second challenge, which was how do we tell different types of flows apart? This is a plot where each dot represents a domain port pair from Microsoft Word. And so when we think about the connections the application makes, we had this intuition that some things are going to be common, like checking for updates, while others will depend on the user, like visiting a specific professor's website. We visualize this by taking each one of these points, counting the prevalence of that flow, sorting that, and plotting it. When we do this, we can clearly see this data has some shape to it. And notice that most of this data, this blue line that are really just small dots next to each other, appear on about one device, while a few of them, where this curve is, appear on many more. And this curve is different for each application depending on its behavior. If we draw a line where the knee of this curve is, we can cut between connections that are common or endogenous to that application versus those that the user could be simulating. We use this to then build some filters that we analyze in some of these upcoming slides. So the first question we looked at was how many of an application's connections are endogenous? Using this filter, we looked at a few different measures of our data set, the number of flows, the number of domains at the second level, and number of ports, and looked at the medians of each of these before and after applying those filters. And what we notice is that there's very few connections that are made by applications that are common across hosts. And so using this endogenous filter can drastically reduce the data set size and make it easier to work with. In the paper, we also show this for things that are a little different, like browsers like Google Chrome. Happy to talk about that more about that during our question section. Our next question we looked at was what applications are not using secure ports? So we generated a list of protocols that use secure communications like HTTPS, and then looked for each application and looked at which flows did and did not use those things on that list. And what we found is that while most endogenous traffic is secure by default, there are notable instances of prominent applications that use insecure communication channels. Things like Microsoft Outlook, Jamf, which is a MDM application, and Trustee. Trustee got some attention this past fall when Twitter and blogs picked up and saw that, hey, this thing that looks security relevant is using HTTP. And we saw that as well. And it turns out that it's by design using HTTP because it's used for certificates, HTTPS certificate status checks. And if it tries to do that over HTTPS, it hits in the loop. And so it has to use an authenticated plaintext protocol instead. We look at all of these more in case studies in the paper. Next question we looked at is, are applications communicating with disreputable domains? An application communicating with disreputable domain could mean as malware or spam or something like that. And so what we did is we looked for domains from popular applications, or I'm sorry. Our next question we looked at was, are applications communicating with disreputable domains? Things like DNS sinkholes that our corporate partners manage, block lists from Snort, a list of domains from a couple different domain generation algorithms, and known spam lists from a corporate feed, a commercial feed, excuse me. And found that none of these things appeared on it, which is great because we don't want things that are really common on popular applications to be talking to these disreputable places. So to wrap up, being able to differentiate exogenous versus endogenous connections for applications drastically reduces our dataset size and gives insight into more common behavior of an application. And most endogenous traffic uses secure communications. Thank you. Everybody.
Thanks, Matt. Sorry, I've got heavy audio dropout here. So this, of course, having some security blood, I really like this paper. If you had wider, and other enterprises, maybe not even of this scale, that had more than Max, are there other tools other than Cisco's spyware that would let you get this rich data set? Or is this a one-off?
Repeat the question. Other ways that we could collect this similar data? right?
Yeah, with other
yeah,
tools
absolutely.
in a heterogeneous environment. That or is this just a
Sure.
one of view?
Yep, there are. These were the tools that our partners had deployed, and so that's what we were able to use. I think it was available for Windows and possibly Linux as well, so it wouldn't just be Mac. But other tools like OS Query can record some of this information depending on what queries you have deployed. So it's not just this one feature that this one product has.
Cool. You didn't catch leakage like from Chrome browser and other such things because I presume you can't deal with the quick TLS encryption, correct?
Quick. So let me repeat the question: is how did we deal with the connections from browsers?
Right. In other words, you call it trustee,
Yep.
Which, well, despite the noise it created on the net, was a legitimate non-encrypted transport. But we have much recent publicity about buzzer, for example.
Sure. So
Is there any hope you could be problem the encryption?
and I think we talked about this a little in the paper too, not quite specifically, but when we were looking at traffic from browsers and really for any of the applications, we had data from two places. One, which was on the host in terms of the like IP address level connections it was making, which I believe Quick and HTTP and everything else would fall into, right? Because it still has to connect to some IP at some point. And then the other place was on the DNS side, which were sensors deployed in the network that we saw the DNS data from. So if it still was having to do DNS resolution for that, we would have seen those connections and those IP addresses, but we didn't specifically look at Quick.
But you did see the connections going back to Google?
We would have seen the connections, yes, if they had to connect an IP address.
From Chrome?
Yes.
Yep. Any questions from the room? Likes it, or nobody else wonders about it. Well, much appreciated. Thank you very much. And I believe we get a short break now.